Dear students, I welcome you all to online classes. I am here to discuss the first chapter of your mathematics syllabus, that is sets. The concept set is one of the most fundamental concepts in mathematics. Knowledge of set theory is very much essential to understand concepts like relations and functions. Set theory acts as a foundation for some branches of mathematics like calculus, probability theory, statistics, etc. Set theory has lot of applications. I think you might have heard these technical words like cloud computing, artificial intelligence, machine learning. In all these technologies, we use sets. Okay. In this chapter, we are going to discuss these things. Set, we are going to see what is a set. Next, we are going to see how we can represent a set, and we are going to discuss different types of sets. And next, after that, we are going to discuss operation on sets. And finally, we are going to discuss some problems based on some standard results. Okay. First, let us see what is a set. In our daily life, we come across certain collections of objects, like a collection of books in your study room, collection of plates in your kitchen, collection of photos in your hall, etc. Now we are going to see what kind of collections are called sets. First, I am going to write the formal definition of set. A set is a well defined collection of objects. A set is a well defined collection of objects. The objects may be anything. They can be books, they may be pencils, they may be persons, they may be anything. Okay. A set is a well defined collection of objects. The object may be anything like books, straight lines, persons, etc. Now we shall take up some examples to understand this definition. Okay. Example number 1. The collection of all natural numbers which are less than 4, is this collection a set? See here, well defined means whenever an object is given, if you are able to say whether it belongs to that collection or not without any ambiguity, then we say that collection is a well defined collection. Here it is very clear that 1, 2 and 3 are the objects belong to this collection. Any number other than 1, 2, 3 doesn't belong to this collection. So there is no ambiguity in this case, that if you are given an object, we can say whether it belongs to that collection or not. Therefore, this is a well defined collection, hence this is a set. Second one, the collection of all intelligent students of a college. The collection of all intelligent students of a particular college. Is this collection a well defined collection? No, this is not a well defined collection, because when we are given a particular students, we are not able to say with certainty whether he belongs to this collection or not. Therefore, this is not a well defined collection, hence this is not a set. Okay. Third one, the collection of all prime numbers. The collection of all prime numbers. Is this a well defined collection? Yes, of course, because we know with certainty we can say what are the objects which belongs to this collection, what are the objects which do not belong to this collection. Okay. So, this is a well defined collection, hence this is a set. We shall take up one more, fourth. The collection of 5 most talented actors of Bollywood. The collection of 5 most talented actors of Bollywood. This is not a well defined collection, because when we are given a particular actor, we are not able to say whether he belongs to this collection or not. Okay. Therefore, this collection is not a set. Okay. Sets are usually denoted by capital letters A, B, C, etc., and elements of a set are denoted by small letters A, B, C, etc. Okay. If A is an element of a set A, then we write that in symbols like this. This is read as A is a member of the set A, or A belongs to the set A. If B is not a member, B is not an element of the set A, then we write that like this: B does not belong to A. This symbol denotes does not. B does not belong to A. Okay. Next, we shall move on to representation of a set. Representation of a set. Representation of a set. A set can be represented in 2 different ways. The first one is raster form or tabular form. Second one, set builder form. In raster form, we write all the elements of the set within a pair of curly brackets, and the elements are separated by commas. For example, let A be the set, let A be the set of all vowels in the English alphabet. In the English alphabet. Okay. Now we are going to express the set A in raster form or in tabular form. We know that A is a vowel, E is a vowel, I is a vowel, O is a vowel, U is a vowel. A, E, I, O, U are vowels in the English alphabet. We have written all the objects or elements within a pair of curly brackets, and we have separated them by using commas. This representation is called roster form or tabular form of the set A. Next, in set builder form, we just write a general element and we state the common properties satisfied by all the elements of the set. So, this is the roster form. Okay. Next, set builder form. In set builder form, we just write a general element x. Okay. Instead of x, you can also write y or any other variable, such that we use this symbol for such that colon. What is the common property satisfied by all these elements of the set? All are vowels in the English alphabet. So, we write x is a vowel in the English alphabet. In the English alphabet. Okay. So, in set builder form, we don't write all the elements of set, we just write a general element and followed by we state the common property satisfied by all the elements of that set. Okay. Now, we are going to discuss some simple problems. Problem number 1. Write the following sets in roster form. Please take down. Write the following sets in roster form. In that first one, A is the set of all x such that x is an integer. X is an integer and minus 3 less than x less than 2. Minus 3 less than x less than 2. We have to express the set A in a roster form. Okay. We know that minus 3, minus 2, minus 1, 0, 1, 2, etc. These are all integers. So, what are the integers between minus 3 and plus 2? Minus 2, minus 1, 0 and 1. So, these are the integers between minus 3 and plus 2. So the roster form of the given set A is equal to set consisting of minus 2, minus 1, 0, 1. Okay. We shall move on to the next problem. Second one, B is the set of all x such that x is a natural number. X is a natural number less than 6, less than 6, less than 6. So, what are the natural numbers which are less than 6? We know that 1 is a natural number, clearly that is less than 6. 2, next 3, 4, 5. So, these are the elements of the set B. These are the natural numbers which are less than 6. So, this is the roster form of the set B. This is a roster form of set B. Next, problem number 3. Problem number 3, C is the set of X such that X is a two-digit natural number such that the sum of its digits is 8, such that the sum of its digits is 8. Okay, so now we have to express the given set in roster form. X should be a two-digit natural number, so that sum of the two digits must be equal to 8. So we shall start with 1. So 1 plus 7 is 8, and 17 is a two-digit number. So 17 is a member of the set C. 17. Next, 26, because 2 plus 6 is 8. 35, 44, 53, 62, 71, and finally 80. 8 plus 0 is 8. Okay, so this is the roster form of the set C. Just one more, fourth one. D is the set of all letters in the word trigonometry. D is the set of all letters. D is the set of all letters in the word trigonometry. Okay, now we have to write the roster form of the set D. We have to write the set of all those letters which are used to construct the word trigonometry. So T is there in the word trigonometry. Next R, next I, G, O, N. Again we have O here. O is repeated twice. No need to write that again in this set. Next M, E. We have already written T, and we have already written R. Next finally Y. So this is the roster form of the set D. Okay. Next, second main, take down. Write the following sets in set builder form. Write the following sets in set builder form. In that, first one, 3, 6, 9, 12. So the given set is in row step form, we had to express the set in set builder form. Set builder form. It is the set of all x such that, see, observe here, 3, 6, 9, 12 are natural numbers and each one is a multiple of 3. So we can write x is equal to 3n where n is a natural number. If I write like this, this means n is a natural number. N belongs to n means n is a natural number. And see here, when n is 1 we get 3, when n is 2 we get 6, when n is 3 we get 9, when n is 4 we get 12. So n must be less than or equal to 4. Okay, n must be less than or equal to 4. N can be any natural number but less than or equal to 4. So this is a set builder form of given set. Next, second one. Second one. Second one, set of all elements 1, 4, 9, so on up to 100. Observe properly, all the elements of the set are natural numbers and each one is a square of some natural number. 1 is actually 1 square, 4 is actually 2 square, 9 is 3 square, so on, 100 is 10 square. So set builder form of this given set is set of x such that x is equal to n square, okay, where n is a natural number. I just write n belongs to set of natural numbers n, and when you put n is 1 you will get 1 square, when you put n is 2 you will get 2 square, that is 4, and at the end when you put n is 10 you will get 10 square, that is 100. So now we are going to discuss different types of sets. In that first one, empty set or null set. Empty set or null set. A set which does not contain any element is called the null set or the empty set. I repeat, a set which does not contain any element is called the null set or the empty set, and it is denoted by the symbol phi, or it can also be written like this, pair of curly brackets. Okay, let us take some examples. Example number 1. Set of all x such that x is a natural number. I just write that in symbols. This means x is a natural number, and x lies between 4 and 5. X lies between 4 and 5. Is there any natural number between 4 and 5? No, there is no any natural number between 4 and 5. That means this set does not contain any element. Therefore, this set is the null set or the empty set. So this set is the null set or the empty set. Example number 2. Set of all x such that x belongs to capital N, that means x is an integer, and 2x minus 1 is 0. That means this is a set of all those natural numbers. set of all those natural numbers which satisfies this equation. Now we shall solve this equation. 2x minus 1 is 0 implies 2x is 1, so x is 1 by 2. We know that 1 by 2 is not a natural number, so it does not belong to n, right? Doesn't belong to n. So clearly this set does not contain any element, therefore this is the empty set. Okay, we shall take one more example. Set of all x such that x belongs to z. Z means set of integers. If I write x belongs to z, that means x is any integer. Okay, and x square minus 5 is equal to 0. And x square minus 5 is equal to 0. That means this is the set of all those integers which satisfy the quadratic equation. Now we shall solve this equation. What do we get? X square is 5, so that means x is plus or minus root 5. Plus root 5 and minus root 5, both are not integers, they are actually irrational numbers, so they do not belong to z. Therefore this set is the empty set. Okay, next, finite set. Finite set, a set which is either null set or consists of a definite number of elements is called a finite set. I repeat, a set which is either empty set or consists of a definite number of elements is called a finite set. For example, the set of all x such that x is a natural number and x is less than or equal to 8. So this set contains the natural numbers 1, 2, 3, 4, 5, 6, 7 and 8. It contains a definite number of elements. Therefore, this set is a finite set. This is a finite set. This is a finite set. So, we'll take up one more example. Set of all x such that x belongs to n and x is odd. Is this a finite set? We know that 1, 3, 5, 7, etc. These are all odd natural numbers. There are infinitely many odd natural numbers. Therefore, this set does not contain a definite number of elements. Therefore, this is not finite. This set is not finite. If a set is not a finite set, then we say it is an infinite set. If a set is not finite, then it is called an infinite set. So, therefore, this set is an infinite set. Infinite set. This set is an infinite set. Okay. Okay. Example number 3. The set of all integers which are more than 100, more than 100. Is this a finite set or an infinite set? We know that 101, 102, so on. This set contains infinitely many elements. Therefore, this set is an infinite set. This set is an infinite set. Okay. We shall take one more example. Set of all x such that x is an integer and x square minus 4 is equal to 0. X square minus 4 is equal to 0. Is this finite or infinite? Now we shall solve this quadratic equation. We get x square is equal to 4, x is plus or minus 2. Plus 2 is an integer, minus 2 is also an integer. Okay. So this set is actually the set consisting of two elements, minus 2 and plus 2. So this set has a definite number of elements, therefore this set is a finite set. This set is a finite set. Okay. Just make a note of this. If A is a finite set, then n of A, if A is a finite set, then n of A denotes the set, denotes the number of distinct elements in the set A. Okay. If A is a finite set, then n of A denotes the number of distinct elements present in the set A, and this is also called cardinal number of A. N of A is also called cardinal number of A, cardinal number of the finite set A. Okay. Next. Next one, singleton set. Singleton set. A set which contains exactly one element is called a singleton set. A set which contains exactly one element is called a singleton set. For example, set of all x such that x is a, if I write z plus, that means z plus is set of all positive integers. Okay. And x minus 3 into x plus 4 is 0. This is the set of all those positive integers which satisfy this equation. If we solve this equation, we get x is 3 or x is minus 4. 3 is a positive integer, but minus 4 is not a positive integer. Therefore, this set contains exactly one element, that is 3. Therefore, this set is a singleton set. Next definition, equal sets. two sets A and B are said to be equal if they have exactly the same elements, and if A and B are equal, then we write that like this. I repeat, two sets A and B are said to be equal if they have exactly the same elements. If they are equal, in that case, then we write like this: A is equal to B. Okay. For example, let A be equal to set of elements 1, 2, 3, 4, and B is a set consisting of 4, 3, 2, 1. Are they equal? Both have exactly the same elements, whatever may be the order of the elements. Okay, we can write the elements of a set in any order. Order is immaterial. So clearly every element of A is also an element of B, and every element of B is also an element of A. Therefore, in this case, A is equal to B. A is equal to B. Okay. Now we shall discuss some problems. Next problem, main. In the following sets, state whether A is equal to B or not. In the following sets, state whether A is equal to B or not. In that first one, A is the set consisting of 2, 4, 6, 8, 10. And B is the set of all x. X is a positive even integer, and x is less than or equal to 10. The question is, are they equal? Yes. See, what is the set B here? Set B is set of those positive even integers which are less than or equal to 10. So better we shall write this set in roster form. So B is a set consisting of 2, 4, 6, 8, 10. Clearly this is same as the set A. Therefore, set A is equal to set B. Next one. Second one, A is equal to set consisting of 2, 3. B is set of x such that x is a solution of the equation x square plus 5x plus 6 is equal to 0. We had to check whether A is equal to B. Okay. Set B is in set builder form. We had to express better if you express B in roster form. So for that we have to solve this quadratic equation. So product should be 6, sum should be 5. So x square plus 5x plus 6 is actually x plus 2 into x plus 3. So that is equal to 0. So further this implies either x is minus 2 or x is minus 3. So set B consists of minus 2 and minus 3. This is not equal to set A. So therefore in this case set A is not equal to set B. Okay. We shall take up one more problem, third one. A is the set of all x such that x is a letter in the word follow. X is a letter in the word follow. Letter in the word follow. B is set of all x such that x is a, sorry, I will take it as y, set of all y such that y is a letter in the word wolf, W-O-L-F. Now we have to check whether A and B are equal or not. So we shall write the sets A and B in roster form. A is the set of all those letters which are in the word follow. So F, O, L, L is repeated twice, so just write only once. O is also repeated twice, just write O once. W. Next, we shall write the set B in set builder form. W, O, L, F. Clearly, the sets A and B have exactly the same elements. Therefore, A is equal to B. Okay. Next definition, subsets. Subsets. Let A and B be two sets. Let A and B be two sets. If every element of A is also an element of B, then we say A is a subset of B. And in symbols, we write that like this. This means A is a subset of B, or this can also be read as A is contained in B or B contains A. I repeat, two sets let A and B be two sets. The set A is said to be a subset of set B if every element of A is also an element of B. In that case, we write that in symbols like this: A is contained in B. Okay. For example, let A be equal to 1, 2, 3. A be the set consisting of the elements 1, 2, 3, and B be the set consisting of elements 1, 2, 3, 4, 5. Clearly, every element of A is also an element of B. Therefore, A is a subset of B. We write that like this: A is a subset of B. Is B a subset of A? No, B is not a subset of A because B has two elements 4 and 5 which are not present in the set A. So, in that case we write like this: B is not a subset of A. We write that like this. We write that like this: B is not a subset of A. Okay, B is not a subset of A. You just make a note of this. Note number 1. Every set A is a subset of itself. For every A. For every set A is a subset of itself. It's obvious from the definition. The null set or the empty set is always a subset of any set. The null set is always a subset of any set A. Okay. Next. Next definition, proper subset. Let A and B be two sets and A is a subset of B and A is not equal to B. Let A and B be two sets. If A is a subset of B and A is not equal to B, then we say A is a proper subset of B. Okay, and B is called superset of A. B is called a superset of A. For example, let A is the set consisting of A, B, C. B be the set consisting of A, B, C, D, E, F. Clearly, A is a subset of B because every element of A is also an element of B. Therefore, A is a subset of B, but A is not equal to B. Here A is called a proper subset of B. A is called a proper subset of B and B is called a superset of A. Okay.